Okay, so good afternoon, everyone. And today we're just going to finish off the last bit about from our class yesterday, and then we'll proceed to start talking about fingerprinting. Okay, so I finished off last time. We've been talking about a gunshot residue, and its real importance in forensic investigation. It very often provides critical evidence, but obviously it has to be very carefully collected. And in order to collect, first of all, you have to know that it's there. It's easy enough if gunshot residue is visible as a mark around a bullet wound or whatever, but sometimes it is not readily apparent. And all surfaces that might have been contaminated by gunshot residue need to be carefully examined, even microscopically, in order to see whether residue is present. But there are ways to chemically test as well, with dyes and things which will reveal the presence of gunshot residue. Remember, we finished off last time by seeing how, for example, hands will be tested for gunshot residue, clothing, and other surfaces around the area where a gunshot was thought to have taken place may also be tested as well. There's one thing to say about testing hands, especially for gunshot residue. This is something which is often omitted in the investigation of a crime scene. One of the reasons being that it may not be apparent in a mass of witnesses and people there and people passing by and everything else. It may not immediately be apparent who is a likely suspect. And in the intervening period before they are identified, they may have time to wash their hands, etc. So very often where gunfire is involved, various people who might be suspect might be tested on the off chance that they have gunshot residue on their hands, rather than letting people walk away and ultimately clean their hands or get rid of their clothes or whatever and have the residue not be found. Now, for collecting the firearms themselves, we are all used to seeing this classic scene in a detective movie where the detective comes in and puts a pencil into the barrel of a gun to lift it and not contaminate it with fingerprints. This is completely wrong. This is never done, and for a number of reasons, which some of them should be obvious to you now. First of all, you could damage the gun. You could damage the barrel of the gun, and by doing that. But much more likely, you could disturb evidence which is present in the barrel of the gun. The reason for this is that when a gun is fired, it instantaneously heats up the barrel. And as soon as that projectile has gone past, all the hot gases have gone past, the barrel begins to cool very quickly and actually pulls in air. And you remember that when we talked about blood spatter, we saw that, for example, when somebody is hit by a bullet, there is forward spatter as the bullet leaves the body, but there's also back spatter from the impact of the bullet. And that back spatter and material from the back spatter may actually be pulled into the gun barrel if the gun barrel is close enough to whatever it is that's being shot. That is called drawback. And drawback very often provides extremely important forensic evidence. That drawback evidence would be disturbed if you were to shove a pencil or something into the barrel of the gun. Instead, usually the barrel of the gun is picked up by the sides of the trigger guard, or maybe by the grip, especially if the grip is structured so that a fingerprint would not be easily left there. But in any case, nowadays, guns are never handled with bare hands. They are always handled with gloved hands. And the reason for that is that our techniques now are good enough that we can actually derive DNA from the barrel, from the grip of a gun. So-called touch DNA may be recovered from the butt of a gun. So it's immediately, it should be apparent that the gun has to be extremely carefully handled to prevent contamination of likely DNA evidence. The gun is carefully examined, it's photographed and everything in place wherever it is found. It is carefully inspected to see whether or not there are bullets in the gun. And if necessary, the gun may be unloaded before anything else happens, just to prevent any accidental discharge. But careful note is kept of the condition of the gun when it was unloaded, etc., etc. In the case of a revolver, very often the investigating officer will swing the revolver chamber out, the cylinder rather out, and they will photograph it and make careful notes about which bullets in the cylinder had been discharged, which were still live, and carefully note their position in the cylinder. Obviously, the gun is one of the most, apart from a body, a gun is one of the most important pieces of evidence that can be recovered, whether from the scene of a crime or from a suspect or wherever. It's a very, very critical piece of evidence, and it is treated extremely carefully, immediately identified, acquires an identity number, and is entered into a very strict chain of custody. So that its fate after finding is incontrovertible, because it may prove to be one of the critical pieces of forensic evidence. Now, legal guns, all legally produced guns, have a serial number on them, and each one has its own identity number, in other words. And that is unique to a particular gun. And it allows the gun to be traced, rather like a car would be traced through the VIN number, its vehicle identification number, can be traced through all its sales, all its points of sale. So with a gun properly, if it's all been done legally, through its serial number can be traced back, its history can be told, its provenance can be determined. And for this reason, criminals will often try to obliterate that number to render the gun unidentifiable. But criminals can very often restore that number. And the reason for that is that the number is punched into the metal. And when that happens, it depresses the forms that we read on the surface of the gun. But in actual fact, that impact distorts metal far below the visible part. So what very often happens is that criminals will file down a serial number until they can no longer see it themselves. But if that metal is treated with acid, it can be stripped away layer by layer by layer until the serial number actually becomes visible again. Even recovery of partial serial number is very, very useful. Now, this is not certain that you'll get the number back, but very, very often you can. So here's one. There's a little tiny short movie, by the way, if you want to watch it, about how this is done. But here's a restored number here. And originally, this was completely obliterated. You couldn't see any numbers at all. They've treated it with acid, one after the other, layer by layer by layer by layer. They treat it with acid, wipe it off, treat it with acid again, wipe it off, etc., etc. And eventually they get low enough deep enough into the metal that the deep distortions of the metal become visible now as letters again. Okay, so we just need to say a little bit, unfortunately only a little bit, because it's a whole topic on its own, about the tool marks. Now, when a gun is a tool, and we've already heard how that tool imparts individual character to the bullets that are used in the gun. That is a typical example of a tool which has acquired its own individual character. The barrel of the gun, when it's made, has imperfections in it, and as it is used, it acquires imperfections. And other parts of the gun, the breech loading mechanism, etc., etc., can all impart markings to the bullets. And that gives the bullet individual marking and gives us the hope that we can link the two. We can link the individual character of the gun to the individual character of the bullet and prove that they were linked to one another. The same principle can be applied widely to many different situations, to many different tools, for example. And I use the example of the chisel. Here is the typical example. Look at the edge of this chisel here, and you'll see that it's buckled and bent and worn and chipped. Each of these imperfections have been acquired randomly. So this tool has now acquired individual character. And if the tool is used, for instance, to prise open a window, or even to stab somebody and a mark is left in bone, which has happened in several cases, those marks, we have the hope that those marks can be linked to the tool itself. And this is a typical instance where individual character of the tool imparts individual character to the marks that it leaves behind. So the same kind of principle can apply widely for many tool uses. And one of the things, of course, that we need to think about is our teeth. What are our teeth if they're not tools? They are tools used for chewing food. And instinctively, we kind of feel or realize that the way our teeth are arranged in our mouth and the damage and everything which our teeth acquire through our lifetime impart individual character to our bite, to the structure and arrangement of our teeth and the mark that they might leave. That mark can be in an object. There was a very famous case, and we won't discuss it, but there was a famous case of murder, which was solved because one of the murderers, one of the perpetrators, was chewing gum and spat it out in the kind of fight and everything. And that gum was recovered long before DNA, by the way, was used. But the gum was recovered with a bite mark in it, and it was linked to one of the suspects. So it's, in theory, at least, we could think about linking things like bite marks to an actual dental structure of a suspect. Now, this had a kind of a heyday of popularity in forensic science from the late 50s on right through to the 1980s. So, and apart from bite marks on food, like fruit or chewing gum, whatever, you can very frequently bite marks are also left on people, on victims, for example, or on perpetrators. And in the struggle, biting is very frequently occurs. And there were several cases where a suspect was linked to a particular crime by a bite mark. And one of the most famous is that of Ted Bundy, the serial killer, who was linked to one of his last victims by a distinct bite mark, which he left, which was then linked to his own dental structure. However, this, I have to tell you, has come under some scrutiny and has become a very controversial topic for the simple reason that when this actually was scientifically tested, it was tested by taking people who were experts in bite mark identification, in forensic odontology, and presenting them with test cases where the experimenters knew the answer, but the odontologists did not know the answer. And the failure rate, this was done by the FBI, the failure rate of those odontologists was so high that the FBI has strongly advised against using bite mark evidence as a definitive. It can inform a case, but all it can do is say that a suspect basically cannot be excluded as the origin of a particular mark. But in fact, the marks made, even by a single individual, are so variable that it is extremely difficult, in actual fact, to tie a bite mark to an individual person. So just realize that this can be used. It can be used to inform a case, but it's not now seldom used as definitive evidence as it has been in the past. There have also been a number of cases, as we'll show you later on towards the end of the course. And there have been a number of cases where people have been wrongfully convicted. It has been proven by DNA evidence that they have been wrongfully convicted of crimes based on bite mark evidence. So it's really an iffy kind of field. More definitive and also very important, because these are so frequently seen, are shoe impressions. And shoe impressions can be left at a scene by for many different reasons. If blood has been spilled, very often people will walk in it and leave clear prints behind. But even on carpets and things like this, sometimes a shoe print can be visualized just because the carpet was dusty, perhaps, or the carpet fibers were depressed in particular pattern. You may need special techniques to bring up an image of that impression. And if the impression has been left because the sole of the shoe was dusty, for example, you may need special techniques for lifting that print using static electricity sometimes, or an adhesive tape or whatever. Nonetheless, examining a shoe print like this does two things. First of all, it gives you class evidence. You can identify from the overall structure and everything. Can tell you manufacturer. It may even tell you a batch number, from which you can work out which retail stores held it. It will give you a shoe size and an idea of the size of the person that was wearing it. It's not going to tell you the sex of the person or any information like that, but it can give you an idea about the overall stature of the person. But that is all class evidence. But a shoe, just like any tool, a shoe is a tool. It's an object which we use to perform a particular service. And like any tool, as we use it, it acquires individual character. First of all, it is individual character because the manufacturing of the shoe is imperfect, and random imperfections are built into the shoe. Second of all, it acquires individual character as the shoe is used, I just want to check something quickly. As the shoe is used, the shoe acquires defects, you mark it, you wear it down, etc., etc. And these are events that occur at random. And because they occur at random, they impart individual character. And if you have a shoe print and a suspect shoe, then you can try to compare the one with the other and compare the imperfections seen. Look at this one here. There's a tear in that bar of plastic or whatever it is, rubber. Here it is here on the test print. Here it is here. Here, this kind of structures, also here, etc., etc., etc. There is a judgment call, however. How many of these do you need to see before you can say these two prints were made by the same shoe? That is very difficult to say. And it may be the subject of defense challenge in court. There's one other thing about shoe prints which is very useful. There is actually a database of shoe prints which you can consult. And the database will give the person, the forensic examiner, information about manufacturers, dates of manufacturer, etc., etc. They don't give you information about individual shoe prints. It's a database of shoe manufacture. Okay, the other thing about shoes is they very often can be recovered in the perimeter, the vicinity of a crime scene, in soil. And so, for example, they may leave a shoe print in soft mud or whatever, which may be spotted. These are carefully photographed, of course, but they can also be cast. And what they usually do is they use a dental cement. They make a mold around the shoe print there, and they fill it with the dental cement, and they end up getting an impression like this, a permanent impression. You must, of course, realize this is extremely fragile and is very easily lost if it starts raining or whatever during the investigation. So this is usually done as soon as possible if there are clear shoe prints available. And that can very easily be compared to a suspect shoe. The same kind of methodology is used also for tire impressions, which are often extremely important at both crime scenes and at things like hit and run accidents and things like that. Same principle applies. The tire has class character because it is manufactured. When it's manufactured, it may have imperfections, which impart individual character, and it wears at random, and that also imparts individual character. They will also, by the way, make this kind of cast for tire impressions in soft soil. Okay, so here is a movie for you to watch about the same topic, called Soul Searching, for obvious reasons. Okay, so now let's move on to a discussion about fingerprinting. One of the most important and one of the oldest of the forensic techniques, which is still used, updated, of course, but nonetheless, the same principles have been used for many years. And all the principles that are used are based upon the work of one particular person, which we'll discuss in a second. I'll just remind you about something. In the United States, this was a very famous case, 1903. In 1903, the United States, most jurisdictions who were doing any sort of identification or logging at all were using the Bertillon system. And at the same time, around 1903, some people were becoming interested in using fingerprints, and there was something of a battle between the two. Many jurisdictions actually opted to use Bertillon rather than pursuing the fingerprinting idea, until this famous case, where these two gentlemen, yes, they are two different gentlemen, and there was confusion about them. They were both called William West. One was Willie West, the other one was William. And one of them was guilty and one of them was innocent. And the poor innocent chap ended up in prison for a crime which the guilty one had committed. Bertillon's system said they were identical people, but they were the same people. He swore up and down that it was not him. And by chance, the guilty one did something else wrong and ended up in the same prison. And suddenly they were presented with this difficulty. And their only solution was to look at the two men's fingerprints to see and try to identify which was which by fingerprints. And they were able to show that the innocent William West had not been anywhere near the crime scene because their fingerprints were different. In actual fact, these men were identical twins. But identical twins, although they have identical DNA, they do not have identical fingerprints because the development of the fingerprint takes place inside the uterus. And it depends on all sorts of things, on pressure that is exerted on the fetus's fingertips inside the womb, and all sorts of other factors. They differ even between two individual twins, two identical twins in the same uterus, have different influences on the development of their fingerprints and their fingerprints are similar, but there are enough differences between them that they can easily be distinguished one from the other. Thankfully, good William West ended up being released. So that case, the William West case, was what put an end to the use of the Bertillon system in the United States. And instead, everybody now began switching over to using fingerprints. And it's based on two principles. The first principle, which is widely accepted, is that no two fingers have identical fingerprints. And consequently, no two people have identical fingerprints, and no two people could leave the same fingerprint. Principle number one. Principle number two is equally important, but we never think about it. And that is that your fingerprint does not change during your lifetime. Its basic structure does not change, except for the fact that you may acquire scarring and marks through continual use of your fingers. But the basic structure of the fingerprint remains the same throughout your lifetime. A fingerprint which you leave behind at a crime scene when you're 19 can be used to identify you when you're in your 60s. Okay, so it stays basically the same throughout. The very first case, in actual fact, which was solved by use of fingerprints was by this man called Folds. And he actually exonerated somebody by fingerprints. The very first accepted case was one where fingerprinting was used to exonerate somebody. There had been a theft and the thief had left behind very clear fingerprints. And they picked up somebody as a suspect. He looked like a very good suspect, but Folds took his fingerprints and compared them to the fingerprints left behind and said, no, these two sets of fingerprints are completely different. And the man was freed. So this was the topic of fingerprints was one which interested evolutionists, by the way, very much. And that was the case for this man, Galton, who was a relative of Darwin's. And Galton did an extensive research of fingerprints, of their structure. He was the first one to provide the basic types of fingerprints, classify the fingerprints, and suggest ways in which fingerprinting might be standardized by taking fingerprints in a particular way, inking the fingers and taking prints, and also advised about how fingerprinting can be classified, gave some information like that. But he was not particularly interested in forensic science. I think he saw its likely use, but he was more interested in fingerprints as a kind of an anatomical curiosity. But this man here, Vukitic in Argentina, he devised the very first workable way of using fingerprints in forensic science. And his system, the Vukitic system, is still used widely throughout South America, but there are various other systems which were developed as interest in fingerprinting developed. So here's the problem with fingerprinting. There are two ways really in which we use fingerprints. The first is, I've said it frequently before, if you've got a very good fingerprint at a crime scene, it's useless to you unless you can tie that fingerprint to someone, right? So how do we do that? Well, there are two ways we can do that. Let's say we have a crime scene and there are fingerprints left behind it. We are pretty certain were left by a perpetrator. And we get a perpetrator, we get somebody who's a suspect of being the perpetrator. Well, we can use the fingerprints at the crime scene and then take a standard set from the suspect and compare them and either exclude them or say, yes, those fingerprints were left by the same person, strongly implying that our suspect was at the crime scene and left the fingerprints. So that's the one way. This other way that fingerprints are used is we have a set of fingerprints, we have a fingerprint or whatever at a crime scene. And instead, we have no suspect. We don't know of a likely suspect, but we have kept a database somewhere of fingerprints, of fingerprint sets. And we can take our suspect fingerprint and we can go and we can compare it to our database and see if we can get a match between. So that is fine, but there's a set of fingerprints for every human being. Every human being has a different set of fingerprints. Just imagine your database. Your database very quickly is going to be enormous. And how are you going to take your one set of fingerprints, say from a crime scene, which may be incomplete? You may only have a finger or 2, 3 fingers, different fingerprints. How are you now going to take that, go to your database and find the match, if the match indeed exists? It would be a very laborious thing to have to sit with your pictures of your fingerprints from the crime scene and then flip through every single set. So instead, what was needed was some way of narrowing the search, of classifying whole fingerprint sets and fingerprints themselves into broad categories where you could say, okay, I don't have to look at 800,000 fingerprints. I only have to look through 600 in order to try and find my match. I narrow my search by setting up classification systems for fingerprints. We put them into a logical, searchable form. In the old days, this was physical. Different precincts might have their own fingerprint database. They might eventually set up statewide and then national databases. But these rapidly became enormous and almost unmanageable simply by the number that were present. Nonetheless, there were fingerprint clerks who were dedicated to that task of effecting the matches and of trying to, they would usually end up producing maybe 10 or 15 likely matches, which could be sent to the investigating officers, and then they would sit together and do a final decision on which set were actually the matching set. But it was an extremely laborious task, and it could take months and months to actually process fingerprints through the system. But that's what they did. There were whole dedicated fingerprint units with fingerprint clerks who did this all day. And they were extremely good at it. They could do it very, very quickly, just by eye, they would flip through fingerprint sets, and their brains were just wired to pick up similarities. We'll find out how the similarities are recognized in a way. In a while, I'm sorry. Okay, so let's have a look at what fingerprints actually are. Have a look at your own fingerprints and check the ends of your fingers, but realize that you have these ridges in your skin, and they are there for a very particular reason. They're called friction ridges, friction skin ridges, and they are part of our grasping ability. But we also have them on the palms of our hands. You also have them on your feet and on your toes. And although they're not widely used, footprints have actually been used in identification, although databases are not kept of footprint. So if you have a look carefully at your fingerprints, this is what you see. Here, these light lines here are the friction ridges. And you can see that they are cast into these particular swirling patterns on your fingers. All of the great apes, by the way, have fingerprints. The chimps, gorillas, bonobos, all of those things, we all have. It's a characteristic of our group, the great apes. So when, again, the basic principles, as far as we know, no two people have identical fingerprints. And I emphasize identical fingerprints. We're going to hear about what that means later on. Then fingerprints remain unchanged throughout your life. And the reason for that is they are genetically determined. The basic structure is genetically determined. But the individual disposition of the fingerprint is set very, very early on in fetal development. And it is set there because the structure of the upper skin is determined by the lower layers of the skin, and they are pressed into their patterns very early on in fetal development, and it stays unchanged for the rest of your life. If we take a section of your skin, this is what like on a fingertip, this is what it looks like. This is the deep layer of your skin here called the dermis. And then here, in this area here, this is a layer of cells which continually divide. And they are cast themselves into these these hillocks here, which are called the dermal papillae. And above it, this is the epidermis here. This is the living outer part of your skin. There is actually on the fingertips, a thin dead layer of cells as well on top. But it's on your fingertips, very thin. Underneath, there's this layer of cells which continually divide, so that these cells continually move up, and you continually shed skin cells from the surface of your skin, but they are replaced from underneath. But they are replaced in the same way for your whole life. They produce these ridges here. And this is the friction ridge. And in the penetrating that friction ridge, there are sweat glands. You can see each of these little dimples here is actually the opening of a sweat gland. That is another way in which we actually improve our grip ability, is by having our fingers are continually slightly damp. In addition to that, the friction ridges continually pick up oils from our skin, especially from the palms of the hands or from your arms. We usually have a thin layer of oils, skin oils, on the fingertips as well, and we continually produce sweat. And sweat largely consists of a solution of sodium chloride, but there are some other things in it as well. There's some proteins and various other things are produced as well. That this is what produces your fingerprint. When you touch something, even if you touch it very, very lightly, you leave behind an impression of the ridge in a mixture of sweat and the oils that are present on your fingertip. And that is the origin of the fingerprint. So the mathematical probability of two people having identical fingerprints is, we just accept that it's very, very small. Galton calculated there was 64 billion different fingerprints. Well, that's way more than there are people ever existed on the planet. So it is just widely accepted that no two people have identical fingerprints. However, there's one case where two people widely separated geographically, one in California and the other in Spain, in a terrorist case, were identified as having the same fingerprint. This poor chap I think in Seattle was suddenly arrested because his fingerprint came up on an international database, and fingerprint experts judged that his fingerprint was the same as a fingerprint found at a bombing scene in Spain. It very rapidly became apparent that this gentleman in Seattle could not have had anything to do with the bombing in Madrid, but nonetheless, fingerprint experts said, no, these fingerprints are the same. This guy has got something to do with the bombing in Madrid because his fingerprint was found on part of the bomb or something like that. It turned out eventually that by the methods of fingerprint analysis, which are currently used, fingerprint experts were saying that the two fingerprints were the same from the same person because they shared enough characteristics that by the analysis of the time, they looked identical. But when you looked at the whole fingerprint, when you looked at all or many differences, it became apparent that they were not identical. The fingerprints were similar, and they were similar enough that by the standards used at the time, they looked the same to experts examining them. But when they were closely examined, it was clear that they were, in fact, from different people. So fortunately, the Seattle man was exonerated. But it's an object lesson. It's an object lesson that we must always be aware that we are limited by the methods we use. Nobody has ever scientifically proven that two people don't share the same fingerprints. And here is a case which came perilously close to a poor outcome because our methods were unable to distinguish that initially that the two fingerprints were in fact different. So let's have a look and see how it is that fingerprint experts actually look at a fingerprint and say, okay, are these from the same origin or not? There are two things to look at on a fingerprint. The first is an overall distribution of the friction ridges. And that is relatively simple to do. You can do it yourself. I'll show you in a minute the different forms. So the first thing is that there are three different kinds. And I'll just show you this one for the moment. This is called a whirl. And you can see it's a spiral shape here, like this. And it's made of these lines here, which all swirl around there and swirl around there and create this whirl. So we can first of all take another fingerprint and we look at it and we say, okay, so here's a suspect fingerprint, right? Come from a crime scene or wherever. We have a suspect in hand. We take their fingerprints, and here is the matching finger. And we see clearly that both of these have whorls. So we know immediately that there is a similarity. They are both whorls. However, many people have whorls on this, and you quite probably do. If you look at your own fingerprints, just the presence of a whorl is not enough. It's important because it's one of the ways we're going to use that forensic scientists use to do that initial classification of fingerprints so that the database becomes workable. But that's not really what fingerprint experts look at in order to determine similarity between fingerprints. Instead, they look for what are called minutiae, very small differences in the structure of the friction ridges, the ridge patterns. And these are the most important ones here. First of all, they look for the position of bifurcations. Here is a friction ridge here, which has divided. Okay, this is called a bifurcation here. Here is a ridge ending there. This here, this little island enclosed here, that is called an enclosure. There. A ridge island is a very small, isolated enclosure. It does not have lead lines. There's one here, sometimes called a dot. There's another bifurcation here. You can come here to this real fingerprint, and you can identify these. Look there, there's a bifurcation there. Here's a ridge ending there. Here's another ridge ending here, etc., etc., etc. So here's our standard. Now we go here to our suspect, and we see how many of these match on this side. Ridge ending, bifurcation is in the same position, yes. Bifurcation here, yes, 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 yes. We start to build up the number of similarities. The number of similarities that are present before a fingerprint expert says, yes, these fingerprints came from the same fingerprint, from the same finger rather, is not something which is hard and fast and determined. It used to be that they looked for 20 to 30 similarities and regarded that as being sufficient to say that both fingerprints came from the same finger. Since the Madrid-Seattle case, that has been increased, and they are much, in fact, most fingerprint experts should be a lot more circumspect in how many they should choose more minutiae before they identify them as being from the same finger. Okay, so looking at an ordinary fingerprint, you can see up to, they will would quickly be able to identify up to about 150 different minutiae, and they are logged very carefully according to their number and position, etc., etc. And it may well be that this fingerprint expert may be called into the court as an expert witness, especially by the defense, to explain how and why they decided that these were the same, especially, I should add, where the suspect's fingerprint, like one recovered from the crime scene, is poor. Because very frequently fingerprints are only partial, and they're called a partial fingerprint. And so only the minutiae for a small area can be determined, and that may be the subject of defense challenge in court. Okay, so the fingerprints at a crime scene especially are often invisible initially. It is invisible to the naked eye. Excuse me. And for some time after they have been deposited, they actually stay slightly moist, and they also preserve the oils and everything which have been laid down. So they may be almost invisible to the naked eye, but sorry, did I have a picture? Okay, they may use special lighting, very bright flashlights shone from the side, for example, ultraviolet light shone on surfaces, All of these things may show the presence of the fingerprint. Once their presence has been identified, they then are usually developed in some way. By that we mean they are usually dusted with a very fine powder, either carbon powder, it's like printer ink powder, or a metal dust. On a dark surface, they may be dusted with a white, light-colored dust. On a white surface or a light surface, they are very often dusted with a dark. The fingerprint can very quickly become visible. The ridges, the oils, moisture, the salts left behind catch the powder, and the ridges become visible as dark or light lines, as distinct lines. That fingerprint very often will be photographed, but the fingerprint can actually be lifted, and it can be lifted with adhesive tape, usually, put onto a card, entered into the chain of custody with careful notes about where it came from. So here's another important principle about fingerprinting. There are three basic kinds of fingerprint pattern, and you can look at your own fingers and work out which you have. You may have the same pattern on all fingers, but very often there are different patterns on different fingers, and there are the three kinds. This is a loop. A loop is characterized by having lines forming the loop, which enter from one side, go around, and leave the same side. If you think about your own fingers, look at them, just imagine a loop, you'll realize this could go towards your little finger, right? Or it could go towards your thumb. It doesn't have to be this way. It could be looping that way. If it points towards your little finger, it's called a radial loop because it's pointing to your radius. I'm sorry, it's called an ulnar loop because it's pointing towards the ulnar of your arm. The ulnar bone is this bone here on your little finger, below your little finger. If it's pointing towards your thumb, it's called an ulnar, I got that completely mixed up. It's called a radial loop. A radial loop because it's pointing to the radius, which is this bone here below your thumb. So if the loop points towards your thumb, it's radius. If it points towards your little finger, it's ulnar. So that's the loop there. This is a whirl, as I've already shown you. Here it is here. And this is an arch there. So they have distinct differences. Look at around, here's the loop is formed by lines there, forming the core of the shape there. There is this line there. Around that, there are framing lines. Look there, follow these lines, ridge lines here, and you'll see they run off on either side, even though these are running off there. These are called the type lines, and there are two sets of type lines. There's one set, this little set here, type lines, and this one below there. So come down here, look at the type lines here. Look at just about the last of these upper type lines there. Here it is there, right? Look at the topmost one of the bottom type lines. There it is there. Where they meet, you see this little triangle there, where they meet. That is called the delta, and it's an important marker for a fingerprint expert. The whirls do not have this type of whirl here is totally enclosed and may be referred to as an enclosed whirl there. It's a kind of circular look to it. Here are its type lines there, has type lines there, and it has type lines there. And as a result, the whirl has two deltas. There's a delta there, and there's a delta there. Here's the arch. The arch differs from both of these because it has lines. It has no core to it. It is formed, and it has no type lines. The whole thing is formed from the lines just buckling upwards like this. So there are no type lines. You can't look at this arch and say, well, here's the top one, here's the bottom one. The lines kind of blend in with one another. As a result, the arch has no delta to it. Loop, 1 delta. Whirl, 2 deltas. Arch, no delta. There are sub-classifications, especially of whirl. There are different kinds of whirl as well. So you can just have a look here at the loop. Here's a print, a little bit easier to see. Here is the core of the loop. And notice this one is pointing in the other direction. Here are the loop type lines that swirl around it. This is loop itself, because the lines are going in one side and out the other. The type lines go, the core lines go in one side and out the same side. The type line goes in one side and out the other, top and bottom. And here's the delta here, where the 2 type lines meet. Loops, again, they have a core, but the whirls rather, also have a core, and the whirl can consist of like concentric circles. That's the one that we saw. But you can also have a whirl. It's still classified as a whirl, which is enclosed by a loop. There's a whirl. Here's a loop enclosing a whirl there. Okay. You can have a double loop. This is like a yin-yang sign. There and there. So effectively has 2 cores. There's a core there and a core there. And this is called an accidental. It means it can't be classified as any of these. And by far the commonest, by the way, is this plain whirl. So now these, all the whirl patterns have type lines, and they have 2 deltas. Now, all of these, loop, whirl, and arch, they only provide us with class identity. They do not provide us with individual identity. The individual identity is conferred by the minutiae, not by this overall structure. But this overall structure, loop, whirl, arch, is very important to fingerprinters because it is on this basis that the classification systems are erected. I'm not going to, if you're interested, you can see one kind of classification system is detailed in your textbook. You can work it out for yourself, for your own fingerprints if you want to. But they are very important because they allow us to categorize fingerprints into small subgroups. A formula is used which looks at the distribution of loop, whirl, and arch on a set of fingerprints, and it allows that set to be placed into a small subcategory so that it makes it easier to compare, especially if you're having to do it by eye. This was very, very important. Here are the arches, by the way. Arches, again, they don't really have type lines because they're formed from the lines themselves. They don't have deltas either. But there are different kinds, and it depends on the degree of folding of these lines. This is a plain arch, and this is a tented arch. It just means very sharp arch, like that. Okay, so the system most widely used in Western countries is called the ACE-5 system. And this is a system which does a 4-step analysis of fingerprints. It first of all does careful analysis of the fingerprints. Obviously, you've got to look at the fingerprint, classify it, etc., etc. That is where the initial classification is done so that we can go to a small subcategory to begin individual comparison. And the individual comparison is done at the level of the minutiae. That's level 2. And level 3 may be proceeded to and not always done if level 2 may be sufficient to identify a print as having come from a common source to a standard set of prints. But in some cases, a level 3 examination is done, and this looks at other minutiae on the print, such as breaks and creases in the whole print, scars, and anything else which has been acquired by the print. Not its innate character, but stuff which has been acquired by the. This basically, level 1 is our classification into subcategories. It doesn't give us individual identification, but it increases the efficiency of comparison. Level 2, we're going to look at the actual minutiae of the print and try to do a firm identification. Can we identify to one common source for both prints? And then level 3, if need be, we proceed to level 3. If this does not, if we, for instance, in a partial print, for example, it might be important to look at things like scars on the fingerprints and that sort of thing. Okay, so let's have a look then at how a fingerprint which is present like on a surface, just visualized, not developed or anything, is called a latent print. And we tend to regard all fingerprints as being latent until they've been identified. The term latent has become very loosely used. So you may see visible prints at a scene in blood, for example, or in some other substance picked up and then impressed on a surface. The blood is quite common. And here is a visible print. It's not actually truly a latent print, it's a visible print here. That print would initially be very carefully photographed together with a scale. And an attempt could then be made to lift it and might have to be developed and then lifted. There are also plastic prints. Plastic prints are prints which are left in a soft substance, like chewing gum or wax or something like that. And I just put this one up for you, which has just come out. This was found this week. This is a little wax statuette made by Michelangelo. And there on the back of it, you can't see it very clearly, but on the back of it there is his thumbprint. It's quite nice to be able to look at this and say, okay, there's Michelangelo's thumbprint. So these plastic prints have been found on all sorts of things, such as in window putty, in wax, on a candle, or melted wax that had flowed on a table, soap. But they can also be left in things like dust. Touching a dusty surface may actually lift dust and leave the impression of the fingerprint behind, and that would be regarded as a plastic print. Okay, so we'll carry on this discussion at our next class, which is on Monday. I just want to remind you, please, that you have your second test, which is on Saturday and Sunday. Okay, it must be completed by Sunday at 11 o'clock. It does not include the section on fingerprints. It includes everything else that we have discussed that has not been tested. Okay, there is a movie here which you can watch in the interim over the weekend if you wish to do so.